Okay, so here we are, ready to create our new project to contain our new unit of measure class. We go to the STEMC Studio homepage, create a new project, and the kind of project we want to create is just the minimal application. We don't need anything special in it, and we'll call this unit of measure. Okay, so you should be familiar with this by now. We have a little bit of boilerplate in here for launching the application. We'll just be using this to do some informal testing of our unit of measure class. But let's move right on to creating our unit of measure class. So we'll add a new file. We'll call it unit.ts. And the first thing you might notice right now is that I'm going to immediately combine the concept of dimensions with units. So I'm sort of flattening my dimensions and units into one class. I think that's going to be good enough for our purposes here. So what we want to do is create a class. We'll call it unit, and we'll give it a constructor so that we can initialize our class. And these are just warnings for files ending in new line, and we want to export this so that we can use it in other files. So we'll put the export keyword in there. And then finally, we need to initialize this with some values that represent our unit of measure. So what we're going to do is we're going to give it a property called m, which is of type number. Number in this case is going to be restricted to an integer. So m is a number, that represents our mass. L is a number, and we'll have t as a number. And recall that we were going to also add the electric current. Now we can implement the electric current either as, we can implement either the electric current, or equivalently we can implement the electric charge. And just for variety, I think we'll do that. Now, there's a simple relationship between the charge and the current, so there's no need to worry about kind of doing the conversion. I mean, a current is just basically a charge flowing per unit time. So we can convert coulombs. We can convert our coulombs to say, well, what's the corresponding sort of ampere value, if we're dealing with a second. Okay, so look at this. This is basically saying that each of these properties is only local. So what I should do is I should put something like either public to make it a publicly available property, or what I can do is I can use, for example, read-only. That'll be a sort of a good hint. And that's probably actually better than using public. Public is actually the default. So we'll just use read-only. And there's our very basic class. Now those people who are, really like test-driven development, I normally like to kind of like just bootstrap a little bit in my code. And I can still get the benefits of sort of eating my own dog food, if you like, by doing a little bit of ad hoc testing just to start with. So here I'm going to import my unit class. I'm going to create const, let's call it mass, equals new unit. And the way that we would create, for example, a kilogram value would be by passing in a dimension value for m for as 1. Okay, so let's print this out now. Yes. Actually, what we're really doing here is we're producing the dimensions of our mass. And you can see that on the right-hand side, we're not getting anything yet because we haven't not implemented the toString method on our unit. So let's go to that, and we'll implement toString. It returns a string. and we can return something. Okay, so we can return, for example, excuse me, $this.m. So I'm going to go for something, you know, very basic now, just to kind of like get us going. M equals that. Excuse me, try that again. L is this. T is this. And finally we'll do Q. Okay, I'll just format that. Let's see. And put space in here. Put space in here. Now, even though you know, I've gone to sort of pains to sort of separate these out, it's still very distracting to have this MLTQ sitting on the right hand side when those values are 0. We just really don't want to have those at all. And in fact, the other thing that we want to do is we really want to have this thing so that it looks a little bit more like, you know, M times L times T times Q with whatever powers are in there. So we want to really have something that perhaps looks more like this. So M raised to the power of that times L raised to the power. And here I'm using the caret symbol as raised to the power. It's obviously somewhat overloaded and has different meanings in different contexts, but this is probably good enough for right now. Okay, and as I said, I don't want to see these zeros appearing on the right hand side, so how can we get rid of that? Well, I think the way to do that is to build this up in parts, each part being a string. So parts is a string array, and we'll initialize it to that. And then what we will do is we will add each part to this array in turn, providing it's non-zero. So if this dot m, so if this dot m is truthy, in other words, it's non-zero, then we're going to push on to our parts. M raised to the power of this dot m. And then at the bottom, all we'll do is we'll just return parts joined with a space. So parts dot joined with space. Okay, and that needs to be a dollar to get interpolation working. So that's the basic idea. Now what we can do is, well, let's kind of go and create a length time charge, right? Mass length time charge M L T and Q, and then we'll just print these out. Length times charge. The length. And we don't expect anything for length because we haven't implemented it. Is time. So I'm kind of like, you know, starting off here with some sort of informal testing. I normally like to sort of just get a little bit bootstrapped before I get into test-driven type development. So let's go and look at our unit. We need to just expand this a little bit. This dot L with L here and here. And length is looking good over here. Do the same for time. Oops. And we'll do the same for charge. Now, those of you that watched the previous theory will realize here that what I'm doing is I'm really building up the dimensions part of the unit of measure at this point. Of course, if I was trying to write out units at this point, then you would see like a kilogram here, and length would be a meter, and time would be a second, and charge would be a coulomb. Okay, but for right now, I'm just going to sort of print out my MLTQ. All right, let's go back to here and let's try to make this do something a little bit more interesting. So for example, if we have a length, then we should be able to multiply that length together to obtain an area, right? So we'd like to do something like this. Area is length times length, and then I'm going to print that out just to see what I've got. So there's my area. Just a little complaint there about trailing white space. We'll get rid of that. Now, we've got NaN. Why do we have not a number? Well, the reason for that is because we haven't yet implemented the operator for multiplication between our two units. And so therefore, it's going to treat this thing as number, and it's going to fail and not a number. So how are we going to do this? Well, I propose that what we first do is we implement a method for multiplication. So before trying to do, before trying to do the operator overloading version like that, let's just try and implement a method called mul. Okay. So there we go. We know mul is not defined yet, so we go to our unit class and we implement the mul method, which is going to have a unit on the right-hand side. It's going to return a unit. And obviously, because we have an immutable class here, we need to return a new instance of a unit. So we're going to return a new unit, and it's going to have various properties, 4 of them. Okay, we haven't used our right-hand side yet. Now that's interesting. We have just put all zeros in to our unit here, and it came out, it computed a unit of 1. Now, what we really want to do is we really want it to be that if something is like dimensionless, maybe the most appropriate thing to print out is the value 1. So I can say, for example, if parts.length is defined, then I want to print out, those things all joined together. And if they're not, I'm just going to print out 1. Okay, so again, this is like informal test-driven development. Okay, but area that value is wrong for area. We want a length times a length. So how are we going to do that? So what we're looking for here is we want to do something like const L equals. We want to compute the exponential value of the L dimension, because in a previous video when we looked at the theory, that's what you do for multiplication. Multiplication is just really addition of the exponents. So what we want to do is we want to calculate this dot L and then add it to the right-hand side dot L and put that in the L slot there. So area is just an L squared. So that's kind of what we want. Now, of course, we need to implement the other multiplications too. So let's just do that as well. So M is there. So that will work for L. For M, let's do T as well. And we'll do it for charge. And so now what we've got is, oops, I need to actually use that. Yeah, so, what we've got is the ability to actually multiply, various things together. So for example, if we go back to here, we could try implementing, well, we can't do a speed yet. Let's do a volume. Okay, so volume. Now, of course, we would be multiplying a width, a breadth, and a depth. So they will be separate quantities. I guess this is a cube that we're actually multiplying together here. And let's go and look at the dimensions of volume. Okay, and that'd be an L raised to the power of 3. All right, so let's go and just improve things a little bit. We want to not be using this long-winded mul method to do our multiplications. Instead, we want to use this operator overloading. So let's go to our project settings. We'll just make sure that operator overloading is actually turned on, which it is. And now we want to go to our class and implement the special method that implements operator overloading. So if you've not seen this before, let's kind of like quickly jump out to our user guide and go to operator overloading. And this explains how operator overloading works. And we want to do multiplication. So we're looking for double underscore mul double underscore. That's the method that we need to implement. Okay, so let's come back. And we want to go to our unit class, and we are going to implement double underscore mul double underscore. And it's actually going to be very much like our method implementation. Now it can start to vary when we do other interesting things, but for the time being, we can just leverage our built-in multiplication. So we can just say this dot mul right hand side. Okay, and that's good. So there's a very basic implementation of operator overloading multiplication. Let's go back. Let's run this whole thing. We've got area. Instead of using the method, let's go and try and do that, and it looks good. So no need to have that anymore. And the volume is going to be a length times a length times a length. And we get L cubed. We could also have gone, a volume is just a length times an area, right? And we get L cubed again. So all looking good. Now, what I'm trying to do is I'm trying to move us along to being able to do something like a speed, which is a length divided by a time. So let's try and do that. So we'll create a speed variable. So speed is length divided by time. And let's print that out. Okay, and for the same reason it doesn't work, we've got NaN. So what I'm going to do here, first of all, is I'm going to implement the method too. The reason why I like to have the method is I like to make it possible for the user to use the method if they want to, and if they don't want to use operator overloading. Obviously, it's not as natural, but there are some environments in which you can't use operator overloading. And so it's kind of like a good practice to understand how to do it as a method and then leverage that method. So let's go and implement div on this, and I am going to put it, it's going to look very much like the mul method. So in fact, I'm going to kind of copy the mul method, put div in here, and if you recall the theory, the way that division is defined, that translates into subtraction of exponents. So what I need to have in here are minus signs. Okay, that will divide this by the right-hand side. And now look, there we go. My speed is L raised to the power of 1 and T raised to the power of minus 1, which is just, of course, 1 over T, right? So, so we're looking pretty good. Let's let's see if we can do something a little bit more interesting. If we've got a speed, then we can multiply that by a mass. And of course, a mass times a velocity is a momentum. Now I'm taking out the geometric part here of my velocity and only dealing with the speed part of it. So this is the numerical value of the momentum without the direction in it. But that's what units are, right? I mean, there is no geometric part in the units. There's only the unit. Okay, so there's momentum, m raised to the power of 1, L raised to the power of 1, and T raised to the power of minus 1. Okay, and we could do force as well. Force is the rate of change of momentum, right? So what we should probably do is implement the div first before we jump onto that. So go back to our operator overloading here. How do we implement division slash slash? It's also the word div, double underscore div. So let's go back to our units and we'll implement that. So here's div, and we'll get to that. We'll just delegate to our div method. Okay, back to our little test bed here. And so speed now, instead of using that, we should be able to say length divided by time. And we get the same value, okay? So now let's try and do force. So force is a rate of change of momentum. So force is equal to momentum divided by time. Now, of course, it's change in momentum over change in time. But since this is a unit, then the change in it's not relevant. Recall the theory, the previous video. And does that look right? MLT to the minus 2, that does look good. And we could even go to energy here. So we know that work is force times distance. So we could say energy is force times distance. Of course, is just, you know, the length. And again, no geometric stuff in here. It's not force times, you know, distance moved in the direction of the force. That's all the geometric part. We're just talking about the units here. So energy, m L squared T to the minus 2. And actually, if you kind of squint a little bit, you realize that L divided by T is L raised to the power of 1 divided by T. So it's L over T. Square that, you get L over T squared, which is a speed squared. So energy is m times the square of a speed. And of course, if you had the geometric factor, the half, in there, then we'd have the kinetic energy. So that's just a little, should convince us that we've actually kind of like got things right. Okay, so that is the basics of how we get our unit of measure going. The next step will be to actually render these as SI units. Okay, so I'll see you in the next video for that. Take care and happy coding.